Backtracking algorithms are used for problems that have multiple solutions, and we want to find all of those solutions. They can also be used for scenarios where only a single solution is needed, but the path to that solution involves exploring multiple possibilities. These algorithms have what's known as decision points, and a decision point is a stage in the algorithm where it chooses between multiple possible paths to explore further. Imagine you're stranded at a fork in the road and you need to get home, but you're not sure which path is going to lead you there. So you just pick one and walk down it until you reach yet another fork in the road. And so you go down one of those. But the one you choose is a dead end. So you retrace your steps to backtrack back to the previous fork and take the other path. You keep going down paths, finding dead ends, retracing your steps, and taking new paths until you find a path that leads you home. Backtracking algorithms work much like this, and it's these forks in the road which are the decision points. We also have something called constraints, which are conditions that restrict the set of possible solutions. They tell an algorithm when it's reached a dead end and needs to backtrack back to the previous decision point and take another path. Backtracking algorithms use depth-first search, so explore right to the end of a path before going down a new one, and it uses recursion to explore all of these possibilities. Depth-first search, and therefore backtracking, can be most simply explained using a maze. We'll use a backtracking algorithm to go from the start of the maze and find our way to the end. When we enter the maze, we're soon met with a decision point. Either go left or go down. The algorithm chooses to go down, and so we follow this path until we're met with another decision point. At this point, the algorithm can go up or it can go right. It chooses to go up, and here we're met with a dead end. This represents our constraint, and so our algorithm knows it can't go any further, and so backtracks back to the previous decision point. Here it only has one option left, go right, and so it follows this path right to the end, until it's met with another dead end, and so backtracks back to the decision point. The options given to us by this decision point have been fully exhausted, and so we must go back to the previous decision point, leaving us with no other option but to go left. At this decision point, we go down, find another dead end, go back to the previous decision point, and go right, following this path until we reach the finish line. Because backtracking is a depth-first search algorithm, we explored each path until the very end before deciding to explore any new paths. If you've previously heard of the branch and bound algorithm design strategy, that's a breadth-first search algorithm, and so in that case we would have explored different paths at the same time. We visualise backtracking algorithms using a state space tree. This is a representation of all the possible states or configurations that can be reached in the process of solving such a problem. The root of the tree is the initial state, and each leaf represents either a solution or a dead end. We'll use the subset sum problem to show how this works. The subset sum problem is a problem where you have an array of numbers and a number called the total. The aim is to find all the subsets of the array such that the sum of all the values in the subset equals the total. Our total will be 10, and the array we are using will contain the numbers 2, 3, 5, and 7. We know that backtracking algorithms need constraints to tell us when we've reached a dead end and therefore backtrack back to the previous decision point. In this case, we'll know we have reached a dead end when the sum of the subset exceeds 10 or we run out of numbers in the array. In this initial state, the subset is empty, and we're currently at the decision point. Do we add 2 to the array or do we not add 2 to the array? The state space tree will explore both of these possibilities, showing us the consequences of every decision we could possibly make. It starts by choosing to add 2 to the subset, and therefore 2 to our current total. The other option it could have taken was not to add 2, and therefore leave the total sum currently at 0. However, because this is a depth-first search algorithm, we're not going to explore the possibility of not adding 2 to the array before we've fully explored all the possibilities of adding 2 to the array. We then continue down this path, adding 3 to the subarray, and seeing that this gives us a total of 5. We then add 5 to the subarray, giving us a total of 10. This is the answer that we're looking for, and so the algorithm stops here and isn't going to bother adding 7 to the array, because we've already found a solution. Backtracking, though, doesn't stop here, because the purpose of backtracking is to find every possible solution. Therefore, we backtrack back to node 5, and see what happens if we don't add 5 to the subarray. If we don't add 5, the total is 5, and then we see what happens if we add 7. Adding 7 leads us to a sum of 12. This hits both of the constraints. 12 is larger than 10, so we've exceeded the total, and therefore know this isn't going to lead to a feasible solution. However, it's not even possible to add anything left to the array because we've run out of elements to possibly add. We therefore backtrack back to the previous decision point and see what happens if we don't add 7. This leads us to a sum of 5. However, there's no more elements to add to the array, and so we've reached a constraint. Therefore, need to backtrack back to the previous decision point. However, we've exhausted all the paths that this decision point had to offer us, and so we go back to the previous decision point, which has also been exhausted, and so we go back to the previous one. We follow this same procedure, going deep to the bottom of paths until we either reach a constraint or find a solution, then backtracking back to the previous decision point to explore more paths. The final result of the state space tree would look like this. Every possible path has been explored, and every leaf now represents either a dead end or a solution. The leaves at the bottom of paths that led us to feasible solutions all hold a value of 10, and so we can go back up these paths to see what numbers led us to these solutions, and therefore see which subsets led us to a sum of 10. For this problem, there were 2 solutions, a subset containing 2, 3 and 5, and another subset containing 3 and 7. To summarise, backtracking algorithms explore different paths, one at a time, until it finds a solution or reaches a dead end, at which point it backtracks back to the previous decision point to explore another path. They use depth-first search and can be represented visually in a state space tree. Leave any questions you want me to answer in the comments, and subscribe if you want to see more related content. Thanks for watching.